Hello everybody, I'm Betsy Romero from Hatari Labs, and today we are going to do a construction of a 2D transform model using MODFLOW, MT3D-USGS, and Flopy. Flopy is a set of Python scripts which can be used to run MODFLOW and MT3D. First of all, we are going to import the packages that we are going to be using today. And for example, we can see that we have NumPy for the creation of arrays, Matplotlib for plotting graphs, and of course Flowpy for MODFLOW. The next lines, which are related to MODFLOW 2005, here we are going to give a name to the model, and at the same time we are going to indicate which executable we will be using, which in this case is MODFLOW 2005. Now we are going to insert the information for the discretization file, and here we can see that the length of our model is 310 meters in X and also in Y. We have the number of rows and columns, both are 31. The number of layers is only one, and the width of rows and columns has been calculated from the previous data. Also, the top of our model is equal to 1 and the bottom is 0, meaning that we have a thickness of 1 meter, so we have created the respective top and bottom NumPy arrays of 1 and 0s, as we can see here. In addition, our model will run for 27 days, so the period length is equal to 27. All these parameters have to be assigned to the discretization package, and this is done with the following line. We can see here that we are adding the name of our model, this one that is here, MF model, and then we will add the number of layers, number of rows, number of columns, all the parameters that we have indicated here. The next one will be the output control. And here we will assign, as the name indicates, the output conditions for the model. In this case, we will leave all the parameters by default, and we will only indicate that we are working with this model name. The next one is the file or the block-centered flow package. This specifies properties controlling the flow between the cells. Here we are going to specify with the Lacon index that the aquifer is confined because this is equal to 0. And also here with tran, we will indicate the transmissivity, which in this case will be equal to 1. As we have been doing with the previous packages, here we are adding to the BCF the name of our model and these parameters Lacon and tran. The next one is the basic package, and here we use it to specify the location of the active, inactive, and specified head cells, and also the initial head in the cells. First of all, here we have iBound. And the I-bound has this, we are going to use a NumPy array of ones where we have the number of layers, number of rows, and number of columns. And since it is equal to 1, it means that all our cells are active. But we want to indicate that along the borders of the model, we will have a constant head. That's why here we are modifying these external cells to, we change them to -1 so they can have this condition. And at the same time here, we are going to indicate that the starting head for the model is equal to 15 meters. So here, if I show you the I-bound, you can see the array that this first line is equal to -1, and also the first numbers and also the last ones, as well as our last line is equal to -1, which will represent the constant head. Now what we need to do is assign these conditions, the I-bound conditions, and the starting head conditions to our basic package. Then the next one is the PCG file, which is the preconditioned conjugate gradient package, which is used to solve the finite difference equations in each step of the MODFLOW stress period. In this case, the parameters we can modify, for example, this one is the maximum number of outer iterations. The next one is the number of inner iterations. The H close is the head change criteria for reaching the convergence, and the R close is the residual criteria, and this last one is the relaxation. The next one, the next package we are going to add is the constant head. Here we can see that we need an array that consists on layer, row, column, starting head, and ending head. Here we are going to define also the location of the constant head in the exterior rows and columns of the model. Here we are indicating this array, and I will show you that with this code we have created this stress period data. And here we have, since we only have one layer, this is equal to 0. And then we have number of rows, number of columns, a starting head and ending head equal to 15. And this is following the same array as with the I-bound, because in the I-bound we indicated that the constant head will be in the borders of the model, and this is where we are indicating also this constant head in the same location. So the next step is to add these conditions now to the MODFLOW constant head. We have again the name of the model, and we need to add this stress period data that we have created here. Then our next package is a well that we will have in the middle of our model, and this is following the same format, but in this case is number of layer, number of row, number of column, and here, sorry, is the pumping rate of the well. And we can see here that the value will be equal to 100 cubic meters per day and will be located, well, in the only layer we have, in the row 15, column 15, and the pumping rate. Also here to the MODFLOW well package, we are adding the name of our model and the stress period data from here. The LMT, which is the link for MT3D-MS for the multi-species mass transport modeling. So this file will help us to make the link between MODFLOW and the MT3D. So we just need to indicate the name of the output file. And our next step before running the flow model is to add the input files to the model, which we will be doing it with this line. It will compile all these individual packages, and after that we will run the MODFLOW model. Here we can see that we have run MODFLOW 2005 and we have a normal termination of simulation. And if we go to our folder where we have been running Flopy, here we have seen that all the input files have been created, and also here we have the list file where here we can evaluate the final water budget. Here we can see that the inflow of the model is via the wells and the outflow is via the constant head. Now we are going to plot the model results using Matplotlib and the binary file utility from Flopy to visualize the results. First of all, we will read the head file. Also, this head file is of the results, and also we need to read the times. Then our next step is to set up the contours and at the same time the extent of the plot. And with these commands from here, we will see the head distribution of our heads. This is in a color scale and at the same time with contours. The next step is to create the MT3D-USGS files. For this, we will repeat the similar steps from the previous part. We will give a name to the MT3D model. We will indicate the version that we are going to be using, which is MT3D-USGS, and the executable file that to be using. And here we will also indicate which MODFLOW model this MT3D has to be connected with. And this is the name that we gave to our model initially, as you can remember. Here we have now the BTN file, which is the basic transport package where we specify the location of the constant concentration cells via an array. The starting concentration, is 0, the porosity is 0.3, and this parameter here is the minimum saturated thickness in a cell. Here we are indicating that the unit of mass is grams, and here we are indicating the IC boundary conditions, where this is similar to the I bound that we indicated previously. We have created first an array of ones, but in where the well is located, we are indicating that it has a constant concentration. That's why we need to change this condition to -1. Now we have the advection package. Here we are going to specify the advection solution option, which we do it with this index. In this case is -1, which means the third order TVD scheme. And also we are going to indicate the Courant number, which is a stability constraint, which will be equal to 1. Also here we add to the MT3D ADV package, we are adding, remembering, in this case is the name of the MT3D model and these parameters that we have here. The next one is the generalized conjugate gradient solver. And here we are going to indicate, for example, the number of outer iterations, the number of inner iterations, and for isolve, the preconditioner is the modified incomplete Cholesky. And we are also adding all these parameters to this GCG file. Now, finally, we are going to work with the sync and source package, where we need this type of array, which is layer, row, column, the source concentration, and the type of sink or source that we are going to be working with. We are going to use this package to indicate that we have a well that is injecting a certain amount of contaminant. For this, we are creating first this array. Also, the location is in the row and column 15, because this is the well, that this source concentration is equal to 1. And we need to indicate that this is a well, so this index will be equal to 2. And also we have to indicate that this is a constant concentration cell, so we will repeat the same array, but this index equal to -1 indicates to the model that this is also a constant concentration cell. So now also we add this data to the sync and source package and we run. Now we are going to as well write the model input files now for the MT3D, and we are going to run the model. Here we can see the information, and we have a program completed. So now we can go here to our folder, and we will see that the MT3D files have been created. We can go here to the list file, and we can see the transport balance, and here this is indicating that the mass, well, the contaminant is entering via the constant concentration cell, while the main exit of the model is the mass storage. Now we are going to plot the concentration results. And here, what we are going to open is this UCN file, which has been created from the transport modeling results. It is here. And we are indicating the time that we want to plot, the color bar, the title, etc. And here we have our result. So I hope you have enjoyed this tutorial, and don't forget to visit our website because we are always posting new tutorials like this one. So thank you, and until next time. Bye bye.